Hey guys, welcome back to the next video. This one is going to be covering the 10 basic organometallic reactions that you guys will be learning. And understanding these reactions will make it much easier to understand the larger reactions you guys will be learning. Those reactions you'll see are essentially these cycles, and each cycle is composed of, let's say, 3 or 4 of these basic reactions. And if you understand them, it'll make the more complicated reactions much easier to understand. All right, and now while you're not going to be required to memorize which of, like, let's say those 3 or 4 little reactions go into that whole cycle for the reaction, you should be able to recognize it if they show you the cycle on the test. And we'll get into what I mean by that in future videos. For now, we're going to dive right into these reactions. Now, what I believe is the easiest way to understand these reactions, besides just slapping it on your index card in this little chart, is simply just reading the name. All right, so we're going to start with what's probably the easiest reactions. So number 1 and 2 are going to be Lewisbase dissociation and association. All right, and so you'll hear these as either Lewisbase dissociation. Another way we can phrase this is going to be ligand dissociation. And same thing for the association is going to be ligand association. All right. So if you ever hear them say ligand association or ligand association, we're talking about Lewisbase. Okay. Now, just quickly, in case you guys forgot what a Lewisbase is something that has electrons, right? It has a lone pair, and it uses that to attack. And so I want to use an example of a ligand you guys learned for these organometallic reactions, something like PR3. This phosphorus has 2 lone pairs, and so it's prone to attacking metals. The thing that attacks the metals, like this, with its lone pair, that's a Lewisbase. The opposite would have been a Lewis acid, something that doesn't really have electrons, and instead it receives a lone pair. It gets attacked by electrons. That would be something like BF3, right? BF3, that boron doesn't have any lone pairs, it would get attacked, or H+. All right, and so let's do an example of what I mean by these Lewis-base dissociations and associations. So I'm going to draw a complex here, and I'm not going to draw in the stereochemistry. It doesn't really matter here. That's not the point of this. So I put a bunch of these ligands on, right? Hopefully ones that you've seen at this point. And what we're going to do is we're going to do a Lewis acid dissociation. Now, what I'm going to do, and I suggest if you're confused about how to figure out electron counting, right, or oxidation states, I highly recommend you you practice that before you continue this video, because I'm going to be using it here, and I'm not going to be showing the calculation. So in this case, our metal is going to have an oxidation state of +3. All right. Now, you've heard the names of the other reaction, right? Of the other reactions, such as like oxidative addition or reductive elimination. Now, whenever you have the words oxidation, right? So oxidation or reduction, we have a change in our oxidation state. In oxidative addition, the oxidation state goes up. In a reduction, your oxidation state goes down, right? Now, Lewis-base dissociation and association, nowhere in that name do I see oxidation or reduction. So my oxidation state should not change. So what that means is my metal, my RH, will have the same oxidation state. It's still going to be RH 1, 2, +3. All right, that is the key here. When you're doing Lewis-base dissociation and association, your oxidation states shouldn't change. And the easy way to remember that is you don't see the words oxidation or reduction in the name. And so that's what I mean by it's easiest to just look at the name. And so what we're going to do is we're going to show the dissociation All right, and so we're going to remove the ligands. We're going to dissociate something. And what I took away is PR3 group, right? It's probably going to be the one right over there. I put that over here. In a Lewisbase dissociation, the ligand we remove must be completely off the molecule, all right? It can't move and, let's say, bind to another part of the complex, let's say to another ligand instead of the metal. No, it has to completely leave. And in this case, we removed this PR3 group. Now, my oxidation state did not change because I removed one of our neutral ligands, right? Our ligands that are not our anionic ligands. So I suggest you get comfortable with which ligands are neutral and anionic. If I removed one, let's say one of these H's, right? These are our anionic ligands. Then our oxidation state can change. And so that was my Lewis-Base dissociation. A neutral ligand comes completely off and no change in oxidation state. My association is the reverse. This PR3 group, we can draw, like, let's say, an arrow over here. It's going to attack the metal right there, RH, and now it's back on the metal. Again, notice my oxidation state does not change from the right to the left. Like, that's because it's a Lewis-Base association. We don't say anything like oxidation or reduction in the name. All right? And so that hopefully shouldn't be too bad. All right? And our number of ligands do change in this case. Obviously, you can see that in this case, if we count, right, I have 1, 2, 3, 4, 5, 6 ligands. In this case, I have 1, 2, 3, 4, 5. And the sixth one was over there. Okay? So you can see we lost one of our ligands. So that's 2 of the reactions down. Now the next 2, these get a little bit tricky sometimes. So this is gonna be ligand insertion / deinsertion. Now another thing you may hear instead of ligand insertion is a migration, and you'll see why. So let's draw our metal. RH, PR3, put some H's here, a chlorine, and what I'm going to do is I'm going to put a double bond. So I'm using a wide variety of ligands here. Again, I just want to expose you guys to as many of these as possible. So we have a bunch of them here. And the oxidation state, which I'm going to just I'm going to write it here. If you want to pause the video and calculate it just for practice, feel free to do so. It's going to be +3. All right. Now, this is a little bit of a tricky sort of reaction, the ligand insertion. And also keep in mind, it's also called a migration, which might be easier to see. What I'm going to do is I'm going to draw a little schematic here that may make it easier to understand. If I have a metal, then I'm just going to write it as M. And I have 2 random ligands. Let's say ligand A. And let's pick orange, let's say ligand B. What I'm going to do is I'm going to just say a statement. I'm going to insert A between B. I'm going to insert ligand A between ligand B. So the way I would draw that is A between B. Let's put the colors back. All right, and now we have A between B. A inserted itself between B. And now B, which used to be bound to the metal, is bound to A. What I did here is the insertion. Or essentially either insertion, or you can think of A kind of migrated between B, or B migrated to A, like this, sort of. And the reverse of it, if I went this way, that's the deinsertion. All right, so keep that little schematic in the back of your head. So now let's try to do it here. The insertion, remember also migration, most often happens with double bonds or like those CO groups into carbonyls. So I'll show it here with this double bond. What's going to happen is here's my metal. My ligands. All right. So what I'm going to do is I'm going to again say the statement. I'm going to insert my alkene between my hydrogen. All right. So I'm focusing on the alkene and the hydrogen. Let's see what that's going to look like. Let's count our carbons again, just to make sure. So we have one carbon there at the end and a second one there. I'm going to draw 2 carbons. And let's number again, 1, 2, and my H. Now in this case, the double bond changed into an alkene. Into an alkane, a single bond. And it put the hydrogen on carbon 2, we can think of it, right? There's no difference really between carbon 1 and 2, but let's just say it went to carbon 2. The deinsertion is the reverse. Let me just delete that. So we have the deinsertion, which is if I took, let's say, this alkane, and I took it away, I deinserted it from away from the H, sorry. Now, what's my oxidation state? Again, if you tried to calculate it right now, you'd see that your oxidation state has not changed, right? So this is still RH3. And here's the way again to remember that. Nowhere in my name of ligand insertion or deinsertion do I have the words oxidation or reduction. That means my oxidation state is not going to change. And now, just to justify it, let's look at our anionic ligands. These are what determine my oxidation state. PR3 are not my anionic ligands, so let's cross them out so we don't get confused. My double bond, the alkene, it's not an anionic ligand. Cross them out. The 2 hydrogens and chlorines are. Each of them are -1. If you sum that, that's -3. Therefore, my oxidation state is +3. So let's look at the right over here. Let me just move this over. Cross out PR3s. They're not your anionic ligands. My H, that's one anionic ligand. Chlorine, that's your anionic ligand. Alkane chains, these are also anionic ligands. If I took this bond and dissociated it onto that carbon, I'm going to get those 2 carbons, that H, and a negative charge on my carbon. So he is an anionic ligand too. So you see I still have 3 anionic ligands. Sum that up, you get -3. And then my oxidation state is +3. All right. And so that's why my oxidation state stays the same. Now, one special type of ligand insertions you guys could see are something called beta hydride eliminations. All right. So what's that going to look like? I'm going to have a metal bound to this H, to this carbon chain, and an H. The carbon bound to that metal is the alpha carbon. Carbon bound to the alpha carbon is the beta carbon. So what I'm going to do is I'm going to try to draw these arrows. All right. Now, remember in organometallic reactions, arrows are a little bit tricky to draw, but we'll try them out. I'm going to take this bond right here and drag it up to form a double bond between the alpha and the beta carbon. And the electrons on this carbon-hydrogen bond between the beta carbon and the hydrogen, they're going to attack that metal. All right. So what that's going to look like, just put this over, metal, hydrogen moved over, right? That took its electrons with it and attacked the metal. And now I have my double bond there. That would be the elimination. The reverse of that is the insertion. All right, so going from here to here, that's my beta hydride elimination. Again, my oxidation state didn't change. All right, let's go to another reaction here. Let's just clear some space. All right, so far we have 4 out of the 10 done. Now, what's our next ones? These are going to be our oxidative addition and reductive elimination. So 5 and 6 are oxidative addition and reductive elimination. Now, these are where our oxidation states change, okay? So this is something we need to watch out for. Again, look at the name, oxidative and reductive. Oxidation means my oxidation state goes up. Reduction means my oxidation state goes down. It gets reduced, right? And the addition part, that says that you need to be adding something. The elimination part says you got to take something away. Oh, and actually one more thing. If you're ever confused the difference between ligand insertion and deinsertion versus, let's say, Lewisbase association and dissociation, I'm going to draw something here that could maybe clear it up. Keeping in mind this same little diagram, the insertion of this would be, the ligand insertion would look like this. A between B. My number of ligands go down, and then the reverse of that, A goes to the metal and B also binds to the metal. That's an insertion this way, and the deinsertion is the reverse. Right now, a ligand dissociation, if I try to draw with these schematics, ligand dissociation, it would look like this. Notice that at the top, right, the insertion, that this ligand is still on the complex somewhere. It's not bound to the metal, but it's still there. Ligand dissociation, it's completely separated from the metal. So that is the difference between the ligand dissociation associations and the ligand insertion and deinsertion. In insertion and deinsertion, it's still on the compound, right? Maybe not, it's not going to be bound to the metal, but it's still there. Whereas if you do Lewisbase association or dissociation, it has to completely come off the molecule if it's dissociation, or if it's association, an entirely separate thing attaches to the metal. All right. Now back to our original reactions over here, the oxidative additions and reductive elimination. So I'm going to draw my compound. So here my metal is going to have an oxidation state of +1. Now this way it's going to be my oxidative addition. Now again, and this is similar for ligand association, I'm going to add a completely separate ligand. So it's not attached to this metal, and then it's going to bind to the metal. That's an oxidative addition. So what I'm going to add are these H groups. So I added this H and this H. Now remember, let's look at our oxidation states. On the left, we have RH +1, right? Why is it +1? Let's look at our anionic ligands. We have a chlorine here. This is a halogen. That's 1. And my PR3s, they're the neutral ligands. So I'll put a 0 next to them. Neutral, neutral, neutral. Now let's look at the right. I have, again, these PR3s, neutral, neutral, neutral. I have a chlorine. That's 1 anionic ligand. And I have 2 hydrogens. Both of them are also anionic ligands. And so that they're also contributing. So on the right, because I have 3 anionic ligands, which are going to be a charge of -3 overall, my oxidation state is +3. So you see, I'm increasing my oxidation state, which is an oxidation, therefore oxidative, and I'm adding something, so addition. The reverse of this is a reductive elimination. You are eliminating something. I'm taking it away. In this case, the 2 hydrogens come off when I'm going right to left. So elimination, they're getting eliminated out. And reduction, because I'm reducing my oxidation state. I'm going from 3 to 1, dropping down. So that's why it's reductive. All right. So keep that in mind. The difference between Lewisbase dissociation and association and the oxidative addition and reductive eliminations is that the oxidation states change. All right. And for doing the additions, separate ligands bind to the metal. That's always going to be the same. And for the eliminations or dissociations, we're going to completely separate them from the molecule. All right. Now, what about our last few? We're almost done. 7 and 8. So these are going to be oxidative. Oh, don't know why I put a Q. Oxidative coupling and reductive. Oh, let's make some room. Reductive decoupling. All right. So hopefully the strategy of like just looking at the name has been helping you guys in terms of, figuring out if it's like an oxidation or reduction, if your oxidation states change. I feel it's much easier to do that than waste your part of your index card writing like a little chart over there in terms of how each reaction changes something. But again, it's always what helps you guys. All right. If you don't find this method too helpful, feel free to find other methods, right? All TAs have their own little methods and tricks that they use. So do whatever helps you guys best. All right. So let's look at oxidative coupling and reductive decoupling. Now, like the name suggests, oxidative, so we definitely have a change in oxidation states. Same for our reduction. So one example, Fe, use a different metal here, so iron this time. So I put these 2 carbon monoxide groups on, and I'm going to put 2 other ligands. Now, when you see double bonds, these alkenes bound to metals, you can see either an arrow, right, or just that, all right? It all means the same thing. And again, let me just move this over actually. And so my oxidation state right now, my iron, it's 0. None of these are anionic ligands. So I'm going to do the oxidative. Let me just shorten this. Coupling. So my oxidation state is going to increase. Now you'll see why. And I think it'll be easier for you guys to see that oxidative coupling is probably a very easy reaction to spot. If they ever ask you to identify it. What's going to happen is these 2 alkenes, let me number the carbons here. 1, 2, 3, 4. They're going to couple. They're going to come together. So I still have those 2 things are bound. But what happens instead is now they look like this. So let's try to number again. 1, 2, 3, 4. All right. So you see still 2 things bound. Here's 2 arrows here. 2 bonds. But what's the difference? These alkenes were neutral ligands. But these carbon chains now we just have regular alkyl groups bound to my iron instead of a double bond. These groups are anionic ligands. If I dissociated this bond to carbon 1 and this to carbon 4, I have something that looks like this. Negative charge, negative charge. So that's 2 anionic ligands, right? So if that's 2 anionic ligands, the overall charge is -2. So my oxidation state is going to be +2. So you see, I oxidized. My oxidation state increased with an oxidative coupling. And the coupling part means that these two ligands came together and we formed this ring. Oxidative coupling is usually very easy to spot because you'll see two ligands come together and they just form a ring. All right, so watch out for any ring forming. And the reductive decoupling, you see your oxidation state goes down from +2 to 0. And the decoupling is a ring breaking. Okay, what you'll often see this with are these carbene ligands. This is what a carbene looks like, carbon, 2 hydrogens, and a lone pair. All right, so oftentimes you'll see them with these carbene ligands, and you'll see some weird thing like this. In one of the reactions you guys will learn later on, we have this double bond, and you have a carbene. Now carbenes bind with double bonds to your metal. They do this weird little double bond thing, all right? And so what they'll do is they'll form a ring with that other alkene, and you'll get something like this. Get this 4-member ring looking thing. You know, number the carbons if it's a little easier. 1, 2, 3, 4. 1, 2, 3, 4. All right. And so you see that would have been an example of a coupling. Your metal here, Ru, 2. And over here, it's going to be 4. So oxidized. And you see a ring forming, got to be coupling, right? So that's already 8. Now on to our last 2. Now the last 2 are a little bit weird. So with our last example is just going to be similar to a ligand association and dissociation, the Lewisbase one. Instead, now we're going to do, let me just change the number here, Lewis acid dissociation / association. All right. Now, these are very rare, all right, and very weird, as Professor Lauer probably told you guys. Now, why are these very weird? They look similar to your Lewisbase ones, right? Except in this case, our electron counts don't change. Why is that? That's because the metal itself is the one that has the electrons. This is a case where the metal itself will be attacking your ligand, all right? And so what is that going to look like? Again, very few, very rare of these reactions. So I'll put this example here. Now, if I did the dissociation, all right, I'm going to do the dissociation going forward. What I'm going to do is I'm going to take the hydrogen off. See, the hydrogen came off, but I'm going to have it as H plus, all right, not that H minus. And what's going to happen is, well, we definitely had electrons here in this bond, right? Well, they're going to be now on the cobalt, right? And we're going to get a negative charge on it. And so this is a very rare situation. On the left, my cobalt is an oxidation state of +1. On the right, it's got an oxidation state of -1. All right, so your oxidation states can change, but the name doesn't really help you in this case. Right? This is a very, very rare reaction. I'm not sure how likely it is to come up on your test, but I would just have an idea of it. All right, because I mean, if it ever comes up, you can always have it at least on your index card. Now, another example of it could be something like this. A ligand like this, BF3. If you're ever confused on if a reaction is a Lewis acid association or dissociation, is just look at the ligand. If the ligand doesn't have any lone pairs to use, then it's very unlikely that it can attack the metal. Well, because it doesn't have any electrons to use. So if it does bind to the metal, it means the metal had to have given up those electrons. All right. BF3, the boron has no electrons. It's only bound to those 3 fluorines. So this is an example of a Lewis acid. And so we can bind it to a metal through a Lewis acid association. Right? And so that would be the reverse of him. It would be the association. Right? And so BF3 or any sort of ligands that don't have electrons, just watch out for them. Now, we talked about those neutral ligands and anionic ligands. So, and not so much Lewis acid ligands. You guys really kind of only know H plus or anything you can identify that doesn't really have any lone pairs. All right, so BF3, H plus, those would be examples of Lewis acids that can be used in Lewis acid association and dissociation. And the oxidation states can change, but this is one example where the name doesn't really help you. But in every other reaction, the name helps you, right? So when you're talking about Lewisbase dissociation slash association, no change in oxidation state, right? But my electron counts can change because I'm adding new ligands or taking them away. In my ligand insertion slash deinsertion, again, no change in oxidation states, but your electron counts can change. In my oxidative addition or reductive elimination, oxidation states change. Your number of electrons change. Ligand number changes. In my oxidative coupling or reductive decoupling, again, oxidation states change. But your ligand count will stay the same. My metal would still be bound, let's say if it was originally bound to 2 double bonds, it'll now be bound to 2 carbons, 2 bonds to form a ring for oxidative coupling. And then for the Lewis acid dissociation slash association, oxidation states change. All right, but like I said, hopefully the name can help you guys. Again, this is my strategy. It made it a lot easier for me when studying for the test, just because I didn't really have to memorize anything then. As long as I can just read the names, I'll be able to tell what's going on. And part of it does involve being able to figure out your oxidation state, all right, which hopefully you get pretty good at just by figuring out what are your negative ligands, your anionic ones. Like on the molecule on the left, I can see that H is an anionic, and my cobalts are all neutral. Not cobalts, sorry, my carbon monoxide ligands. And therefore, I know that the oxidation state is +1 because the hydrogen contributes a charge of -1. All right? And so hopefully this video made it easy for you guys to understand. I know that this stuff is a little bit tricky and a lot more different in terms of the stuff you've seen thus far in organic chemistry, but with practice, it'll be much easier. And I'll see you guys in the next video.